Welcome to today's Explainer. We are jumping right into one of the absolute coolest phenomena in all of physics, the microscopic mechanism of how certain materials can achieve completely zero electrical resistance. Seriously, imagine a power grid that literally loses no energy, or floating trains powered by perfect magnets. That's the real-world promise of superconductivity. So today, we're going to unpack the mystery of how this actually works down at the quantum level.
To really get this, we first have to confront a massive paradox. Basic physics tells us that negatively charged electrons naturally repel each other, right? They inherently want to push away. And yet, to achieve zero resistance, these microscopic loners somehow manage to perfectly cooperate. How in the world do particles that are essentially hardwired to repel each other suddenly team up to glide through material without losing even a fraction of energy? That is the exact question we're going to answer for you today.
All right, let's set the stage. Take a look at the normal state at room temperature. Electrical resistance happens because electrons flowing through a conductor are constantly crashing into thermally vibrating positive ions in the material's lattice. It's just a bumpy, chaotic ride. But then, look at the superconducting state, which kicks in below a very specific critical temperature, or TC. When the temperature drops that low, the thermal vibration drops right along with it. And it's this reduced agitation that completely changes the game, allowing for a totally new type of interaction between the positive ions and those negative electrons.
Now, historically speaking, this puzzle took decades to actually solve. H.K. Onnes first discovered superconductivity way back in 1911. But it wasn't until 1957, which is almost 50 years later, that scientists John Bardeen, Leon Cooper, and Robert Schrieffer proposed the very first successful microscopic theory. We now call it the BCS Theory, named after their initials. It was such a monumental, game-changing breakthrough in explaining this quantum mystery that the trio took home the Nobel Prize in Physics for it in 1972.
Okay, so to really grasp the BCS theory, let's do a super quick refresher on our quantum cast of characters. First up, fermions. As you likely know, these are particles with a half-integral spin that follow Fermi-Dirac statistics. The absolutely crucial takeaway here is just this. Electrons are fermions. They're the individual, solitary actors moving through our material.
On the flip side, we have bosons. These are particles with a whole number spin that actually love to share the same quantum state. Now, while photons, or particles of light, are probably the most famous example you know, our focus today is on a totally different boson, the phonon.
So what exactly is a phonon? Well, you can think of it as the elementary excitation, basically the quantum unit of a vibration inside a crystal lattice. When the atoms in a solid vibrate, that vibration travels as a wave. A phonon is simply the quantum mechanical way of describing that wave of vibration. Keep this in the back of your mind, because the phonon is literally the missing puzzle piece to solving our zero resistance mystery.
Let's look at the microscopic architecture here. As our negatively charged electron begins to move through this positive lattice framework, the dynamics completely change. In a normal state, it would just crash around randomly. But remember, we are at an ultra-low temperature right now. Those intense thermal vibrations have quieted right down, which perfectly sets the stage for something genuinely remarkable. Let's slow down this microscopic choreography step by step. As the first electron zips through, it subtly attracts the positive ions in the lattice. Because the heavy ions react so slowly to the fast-moving electron, the lattice actually distorts inward, momentarily creating an area of higher positive charge, kind of like a positive pocket. And here's the kicker. Before that pocket can relax back to normal, a second electron comes along and is powerfully pulled right into this concentrated positive area.
Check out the exact moment of matchmaking here. The first electron warped the lattice, and then the second one chased that newly created positive pocket. The positive lattice is basically acting as a microscopic middleman. By utilizing the lattice in this specific way, these two mutually repelling electrons have actually become attracted to one another. They're now intrinsically linked.
We actually have a very specific name for this newly formed bond, a Cooper pair, named after Leon Cooper of the BCS team. A Cooper pair is precisely this, a pair of electrons in a superconductor that become attractively bound together. What's super important to remember here is that for this pairing to be stable and actually work, the two electrons must have equal and opposite momentum and spin. They become a perfectly balanced tandem. Zooming back out to the macroscopic scale, the BCS theory states that superconductivity is ultimately caused by a condensation of these Cooper pairs. Because these two solitary fermions, the electrons, have teamed up, they now act collectively like a single boson. Millions of these newly formed pairs condense into a single, unified quantum state that just glides through the lattice, completely unbothered by scattering. They have completely overcome Coulomb repulsion, and electrical resistance literally vanishes. This is the microscopic magic that makes those lossless power grids and floating trains a reality.
Now, if we view this through the strict lens of quantum mechanics, this coupling isn't just some physical distortion. A Feynman diagram reveals it as an exchange of phonons. The first electron interacts with the lattice, essentially emitting a phonon. The second electron then absorbs that phonon. This exchange is the fundamental glue holding them together.
And it's just a beautifully balanced transaction of momentum. Electron 1 arrives, creates a phonon, and elegantly alters its path. Electron 2 sweeps in, absorbs that exact phonon, and adjusts its own course. The momentum lost by one is perfectly gained by the other. It's an incredibly elegant quantum handshake that seamlessly binds them together while perfectly obeying the universal laws of physics.
Now, as brilliantly constructed as the BCS theory is, it's not the final chapter of our story. We've got to acknowledge its limits. The original BCS theory perfectly describes what we call S-wave superconducting states. These are totally the rule among conventional, low-temperature superconductors. But nature always throws a curveball, right? We have since discovered unconventional, high-temperature superconductors known as D-wave superconductors. And unfortunately, that beautiful lattice phonon exchange we just explored doesn't entirely apply to them.
Scientists have definitely tried to create extensions of the BCS theory to describe these high-temperature cases, but so far, they just remain insufficient to completely explain the observed features. That said, do not underestimate the profound impact of the BCS theory. Its mathematical framework is so robust that it's literally utilized in nuclear physics. It perfectly describes the pairing interactions between nucleons, the protons and neutrons, deep inside an atomic nucleus. The underlying math of this cooperation is universal.
Which really leaves us looking toward the horizon. If the BCS theory brilliantly unlocked the secrets of low-temperature zero resistance, what completely new theories or quantum mechanisms are we going to need to finally unlock the secrets of high-temperature superconductivity? Just imagine a room-temperature superconductor where we don't need any expensive liquid cooling. The scientist who solves that puzzle will absolutely be claiming the next Nobel Prize. Thanks for exploring this quantum mystery with us today. Keep wondering and keep exploring.